Hello. So in this lecture, we are going to discuss chapter 17, heap sort. Okay. And we already discussed binary tree. Okay. And the heap sort is built upon a concept called complete binary tree. Okay. So what is a complete binary tree? So it's a binary tree where all non-leaf nodes must have two child nodes. Of course, if there are enough nodes, okay, we will see the case that just has one child nodes, okay. And but there is another requirement is the leaf nodes must be filled from left to right. Okay, you must fill like this. Okay. So it's a binary tree. Didn't say it's binary search tree. Okay. So binary tree. And the non-leaf node must have two child nodes when we have enough nodes, okay? And the leaf node must be filled from left to right, okay? So let's take a look. So for the first case, yeah, each node, non-leaf node has two child node, and all nodes, leaf nodes filled from left to right. So this is a binary, complete binary tree, okay? For the case B, yeah, we can also see each non-leaf node has two child nodes, but not node 9 because we don't have another number to fill here, etc. So that's okay. But all leaf nodes also fill from left to right. So both of these two cases are complete binary tree. Okay, and then let's take a look at this case. Okay, for this case, we can see for all of the non-leaf node, yeah, they do have two child, so that condition met. Okay, but let's see for the leaf node 7, then it's not is supposed to go to left, but it's go to right. Okay. So it didn't meet this condition, fill from left to right. Okay, so that's why this is not a complete binary tree. Okay, and then for this case, let's see. For this case, then node 9, we have extra nodes we can fill, we can add here, but it doesn't do that. So this node 9, it just has one child instead of two, even though we have enough nodes. And on the other cases, the leaf node not filled from left to right. So that's why this is not a complete binary tree. Okay. So complete binary tree concept we understand. Okay. So we have another new concept. Okay, we call it minimum heap tree and maximum heap tree. It's a mini heap data structure and maximum heap data structure. So a new data structure. Okay, so for this mini heap or maxi heap, one condition is it must be complete binary tree. Okay, complete binary tree. So that's the first requirement. Then there's another requirement on top of it for mini heap. The requirement is every node is also arranged such that it contains the minimum value in the subtree rooted at that node. Okay. So let's take a look at this case. Okay. So for this case, for the root node, okay, 5, yeah. So its minimum value is it in the subtree, okay? In this tree, it's minimum, so it's at this root node. So that's 5, okay? Then let's take a look at this subtree. So 6, yeah, it's a root for this subtree. It's minimum value, so it doesn't meet the condition. And then let's take a look at this subtree. Yeah, and it's 9 is at the root of this subtree, and it's a minimum value. Okay, so and then for the leaf node, we don't need to worry. Okay, so this also meet the conditions, the minimum value in the subtree rooted at the root at the node. Okay, so similar analysis for the case B. Okay, so both of this are mini heap data structure. Okay. And with this kind of special arrangement, then there is a benefit when we do implementation. Okay. So if you recall previously when we discussed binary tree, binary search tree, AVL tree, their implementation using linked implementation, is it? But for heap, the mini heap or maxi heap, there is a special feature that when we implement it, we can use array style data structure. Okay, such like array list. Okay, so it's a better choice than linked implementation. Okay, and why we can do it? Because it's a complete binary tree. Okay, and because of the complete binary tree, so then the data structure allows for efficient access to the element using array. So we can take advantage of indexing operation, okay? And there is a relationship in heap, okay, between the indices of a node and its children. Okay, it's a pretty straightforward. So if a node is at index key, okay, then its left child's index going to be 2k plus 1, and its right child index can be is 2k plus 2. Okay, so there is this kind of special relationship. Okay, so that's why it needs to be a complete binary tree. Okay, so that we can maintain this kind of relationship using array. So keep this in mind, okay, for the complete binary tree, for the mini heap and maximum heap, then we can use array for the implementation. It's more efficient. And then we can take a look, okay. And it also says, okay, in the above defined relationship, is it if the calculated left child right child index is greater than the size of the array minus 1, then that means the child node doesn't exist, okay, because it's array that has size, okay. We can also verify here, so node 5, okay, its index is 0. So 6, then it's going to index it's 1. So 2 times 0 plus 1. 9 is a right child, so 2 times 0 and plus 2, so it's 2. Okay. We can see, so sub 0, sub 1, sub 2, is it? And then for node 16, so it's parent child's index is 1, so 2 times 1 plus 1, so it's 3. Okay, for 11, so 2 times 1 plus 2, it's 4, is it? Yeah, so same thing for 20 and 25, we can calculate. Okay, so it clearly shows us the relationship, and also because of the areas, it's also using the index, it can help us to figure out the level of the node. in the tree. So quite convenient. Okay. Okay, then for an existing heap, if we add a new number, is it add a new node to the heap? How do we do it? Is it and so this is mini heap. Is it so? Suppose we want to add 7. Is this where 7 is going to be added? Okay, we also need to meet the condition from left to right when you fill. Is it at the leaf node case? Then for node 3, it is a parent node, so 2 times 3 plus 1, so it should be at index 7. Is it? But then after we insert as a leaf node, we also needed to maintain the mini heap. So the parent node, so each node for its subtree, it should be the minimum value. But if we compare, this doesn't meet the condition, so we needed to swap those. So we place 16 here and we're going to put 7 here. Is that? And then we check. Is node 6 the minimum value among its subtree? Yes. Okay. And then all of the other still maintain. Okay. So we need to do swap that to keep the minimum requirement. Okay, then let's take a look, another look. Node 0, that, okay. For node 0, then when we calculate it, it should be the parent node for node 7, that. So we are going to insert it as its right child, that. So at index 8. But after we insert them, same thing, we need to maintain that minimum requirement, that. Okay, and so we need to first we need to compare with its parent node. We can clearly say that so 0 is greater is less than that. So we need to swap them. So we put 7 here. 7 here and then 0 here. Okay, and then we need to compare with its parent. That we can clear it's still less than, so we move 6 down here and put 0 here. And then we need to compare with its parent. That we can clear it's still less than, so that's why we put 5 here and put 0 here. Okay, so now if you check, then every node meet that condition. So after we do the insert, then we need to do each of the subtrees recheck to meet the mini heap requirement, is it? So this kind of operation we call it a heapify. Okay, heapify. Okay, so to maintain its mini heap requirement. Okay, so that's about how do we insert. Okay, and then next, let's take a look. Node 23 after we insert. Then we can see, yeah, we should insert at index 9 here. So the left subtree of node 11. Okay, now after this, we can see, yeah, the tree is still a mini heap tree, so we don't need to do anything. And this is the array, okay, for the mini heap. So we can see for the heap, if we use array to keep track of the tree, it's quite convenient, okay. Okay, and if you recall for chapter 20 when we discussed AVL tree. At the end of the discussion, we showed the two Grand Sand dune photos about the national park, from the national park. So that national park is Grand Sand Dunes National Park, okay, and it is in Colorado and very beautiful. Okay, so that's the general concept about mini heap and maxing heap. And next, let's take a look. How do we do heap sort then using the heap concept? Okay, so here, let's see. Okay, here. And so suppose we have this sequence of number. Okay, we have number 9, and then number 11, number 6, number 16, number 5, number 20, number 25. Okay, we want to sort them in ascending order. Ascending order, okay, using Heapsort. Okay, so how do we do that? Okay, so first, let's build a binary tree first. Okay, so we do 9, and we using the using array that, and then follow it should be 11 and 6. Okay, and then next to it, we follow the rule, is 16 and 5, and then 20 and 25. Okay, and so this is the original array. And with its index sub 0, sub 1, okay, something like this, okay. But to sort in ascending order, we needed to build the maximum heap. So this definitely is not the maximum heap, okay. So we will start with the last non-leaf node. So it's node 6, okay. And so we needed to compare with its children. So definitely it's smaller. So we needed to swap it with 25 and 6, okay. And then we needed to move up because it's a change, okay. So 25 definitely is larger than 9, is it? So we need to heapify 25 and 9 here, is it? Okay, so similar here. Oh, I let's we do level by level. So 9, then 11, 6, and then 25. Okay, so we already swapped 25 with 6. Okay, so this pair with, and then we need to check the next one, 11. Then 11 and 16 with the child. So we need to do swap. So 16, we move up, and then 11, okay? And then we move to the next level, is that then level, the top level 9. And then we can clearly see we needed to swap 25 with 9, is it? So this procedure from bottom up, is it? We keep doing swap to build the maxing heap. We call it a heap 5. Okay, so now the array then changed to 25, is it 16, 9, and then 11, and 5, and 20, and 6, okay? So how do we do the sorting, heap sort? So the idea is then we are going to move. So 25 is the largest, is it? Move, swap it to its supposed location. It's supposed to be at the last slot in the array. So we are going to swap these two. So 6 and 25. Okay. So in the heap, then we needed to swap it. So 6 and then 25. Now 25, it's already at its location, is it? So it's already sorted. So this one is sorted. So we don't need to worry anymore, is it? So we only needed to consider this part of the tree, okay? So after we do the swap, we can clearly see it doesn't meet the maximum heap condition, is it? So we are going to do the heap find again, okay? So we start from the last internal node, is it node 9, and then compare it with its subtree, is it? So clearly we see we need to do the swap. So 20 and 9, is it? For this part, we didn't do anything, so we don't need to do anything. And then for the node 6, we move to the next level, is it? So we can say we do need to swap between 6 and 20, is it? Yeah, so we need to do so now it's 20 and 6. Oh, in my previous discussion, I made a mistake. Okay. Yeah. So now 6 is here. Is it? So heap 5 is from bottom up. Okay. To do the swap, to move the value to its right location. But after we do the swap, because we change the value, we also need to maintain it as a maximum heap. Right now, it's not a maximum heap, is it? So we need to continue swap node 6 and node 9, okay? So this is 6, we move to node 9, okay? So this process then is from up to, we move down, is it? Move down. So this is, we call it a shift down. I'm sorry, previously I forget to move 9 down, okay, with 20. Okay, so, but anyway, so we needed to move 6 down and 9 up, okay. So now this is a maximum heap, okay. Now with this maximum heap, so the array now change it to 20, and then 16, and then 9, and then 11, and 5, and then 6, and 25. And previous we know 25 already sorted, is it? And now 20 is the largest for this subset, is it? So we need to swap it to its location. So we need to change it to move 6 to the first and the 20 to the second to last. Now both 20 and 25 are sorted, is it? Okay, so now 6 is here. 20 is 3. So both 20, 25 are sorted. So now the tree changes to 6, 16, 9, 11, 5, 20, and 25. And this part is already sorted. Okay. So the new array changes to 6, 16, 9, 11, 5, 20, 25. These two already sorted. Okay, and after we do this swap, then we can clearly see this tree is not a maximum tree, so we need to do heapify again, okay? So let's do heapify, okay? So heapify, then we need to compare 6 with 9, and also 6 with 16, is it? And we can, oh, yeah. And then we can clearly see we needed to move 16 up and then move 6 down. Is it? After we move 6 down, then we can check this subtree. And then for this subtree, then we need to do another chain. So 6, then 11, okay? And now we can see, yeah, 16 is the largest, and it's at the root. It's a root node, so that's fine. And so the new array now change it to 16, 11, 9, 6, 5, and 20, 25. And we already know 20, 25 already sorted, is it? And the 16 is the largest, so we need to swap it to its location. So we move 5 up and 16 here. So now 16, 20, and 25 are all sorted, okay? So now we needed to change this to 5 and change this to 16. So now 16 also sorted, okay? So after we move 5 up, okay, we need to do the heapify again, okay? So we need to swap it with 11. So here is 5, here is 11, okay? And then after we move 5 down, and then we see. So we need to do the sift down. Okay. And then we see we need to swap 5 and 6. Okay. So the new tree now change it to, we can do the remove this part, too messy. So let's change it to 11, and then 6, 9, and this is 5, 16, 20, 25. And we know all these 3 already sorted, is it? And the new array change it to change it to 11, 6, 9, 5, 16, 20, and 25. And we know of the last 3 already sorted with it. And we needed to swap 11 and 5. Okay, so 5. And then here is 11. Okay, so we need to swap 11, 5. So now all of this last 4 sorted. Okay, and then for this uh, subtree there. We need to check, is it? And definitely it's not a maximum heap, so we needed to heap 5 again, is it? So we move 9 up and 5 down, okay? So after that, then, so 9 is here, 5 is here, is it? And after that, we needed to move 9 to its, because 9 is the largest, is it, in this heap. So we needed to swap it to its location. We move 5 here and 9 here. So now the last 5 items are sorted. Okay. So we move 9 here and then 5 here. Is it? So now the sorted range spanned to from 9 all the way to 5. And then we just have the last 2 numbers, and we can clearly see that you can do it again, and move 6 up and 5 down, and then because only 2 numbers left, is it? So we need to move it to its location, and then we know, okay, 6 at its location, and then 5. That's it. So we are done, and the whole list is sorted. Okay. So this is how we do heap sort. Heapsort. Okay, so it involves the heap file, and at the same time, we also need to zip down to maintain the maximum heap. Okay, so that's the idea about heap sort. Okay, so that's the discussion for heap sort. And in our next lecture, we are going to discuss another topic. See you.